Hi, this is the first of several videos on digital circuit and systems about, specifying, planning, developing and testing a typical RS latch type, 74LS279, a set reset typical latch. It can have several symbols, the typical one where R and S are active high. Then there is this other one that includes the output Q not, as another possible output. And there is this one here where you see that it is the same functionality, but now set and reset are when activating them with a 0. So you have three conventional symbols, but the truth table is the same all the time. We're respecting the activating logic. So if you have a table like this where R and S looks like active high, if 0, 0 happens to be not active, you see when R and S happens to be 0, 0, you keep the value. In the next state is for keeping the value. If you are driving the S, you like to save a 1. If you are driving the R, you like to save a 0 in the cell, and 1, 1 is not defined or not permitted or undefined, as you like, okay? So let's go explaining, how to use that by means of a timing diagram. So this is the main objective now. Let's describe an RL cell like this from this specifications point of view, which means that now from the function table we have to be able to draw a timing diagram. Okay, so let's see how can we go and discuss the specifications of the reset set latch device. A 1-bit memory cell, okay? A 1-bit simplest memory cell. Let's see how can we discuss that. Well, the block is like this: 2 control inputs, to to decide what is going to happen with the value Q. And that means that this circuit can be inferred, thinking about the reset and set inputs, and then guessing or establishing the value at the output Q in the future. So this is the next state, or the next value in the future, with this idea of memory. Okay, you have this idea of keeping a 1 and keeping a 0. This is the idea of the R and S. So it may happen that you are not driving R and S. So this is when you keep the previous value. If you have the intention to set a 1, to write a 1, this is what you are going to do. You are driving the set to save a 1. Okay, you do nothing, you see. If you do not drive any one of the inputs, if you like to do nothing, but keep the previous value. So in the future you keep the previous value, or like this, you like to, you see, you are driving the R, so what you like to do now is to save a 0. And the situation where you like to drive the 1 and the 0, the set and reset at the same time, this is not defined, because in some way in this simple device has no meaning. You like to write a 1, write a 0, or keep memorizing what is already stored in the queue. It is that simple. Okay, so this is the symbol and this is the function table. One device like this that you can just go and browse in the datasheet is the 74 LS 279. You have, perhaps they are active low, but doesn't matter. You have four latches like these in the same classic chip. So, well, what is that goes next? Okay, what is that goes next? If you know the symbol and you know the way it works, you know that what goes next here is establishing this functioning of the circuit in time. So you better go and draw an example of timing diagram, right? An example of timing diagram, something like this. So you will drive in time the input R and the input S. You know, this is what we call reset, and this is what we call set. So this is what we will drive, and we will investigate the value of the Q, you know, in time. And in this way, we will very well be aware of what is the present, what is the current state of the device, and what will become the next state to go, and how this new state is going to be settled to be the current state. So we do as usual, okay? We drive the control inputs with ones and zeros. So this is very possible here again. You can imagine that now is your turn to drive as R, now even for a longer time, something like this. Here you driving a 1, and then here you driving a 1 again, and here perhaps you drive a 1 again and then go to 0. So this is a typical R and S driving situation. So now, in order to establish the queue, you better do that thing of establishing vertical timelines. You know, you can better take another color, because you know that is the fundamental idea here. We talk about, you know, that kind of vertical timelines that in the EDA tools we associate with cursors in the timing diagram, so we can move around and we can see what happens in every situation, because you see in time the system is driven using different ones and zeros. So that happens to the end. Every time that you have a change, you know, you have a edge, some signal that goes, you know, from 0 to 1 or from 1 to 0, you have to have a different output if that is the case, okay? So that is the way it works. You organize some R and S stimulus, pretty much the same thing that you will do when driving this stimulus as a process in the test bench stage. But now it's that way. So what you have to do, attending this truth function table, is to calculate the Q. This is the typical problem, and this is the way to establish in time what is going to happen. So, for example, you take another color, and now you say, well, 0, 0, right? And this may be t equals 0, but you know, 0, 0 means that the system is doing nothing but keeping the previous value. But if this is time 0, who knows? Okay, who knows what is going to be in the circuit before the time zeros, because this is a digital electronic circuit. This is the ground reference. The circuit is connected to a power supply, VCC, for example, 3.3 volts. Okay, or if this is TTL circuit, this is 5 volts. So here you will very well find any value possible when you what? When you switch on the circuit. So normally the electronic devices are associated to a switch, and for example this switch is on, you see, at time equals 0. Now is when you are connecting the power supply at time equals 0. So now is when the system is going to start doing something. Let's see. But before this time, or even at this time and on, if you are not driving R and S, the system do not know what to do but to keep the previous value. So which was the previous value? No one knows. So the system has an uncertain output, an unknown, you see, up to this point. And now what? Well, now the instructions are very clear. For all this time, you see, in this fraction of time, you see, in this time slot, what you are doing is driving a 1 and a 0. So that is a very clear order in the function table. This is what you do, 0, 1. If you do that now, the output is settled to be 1, that way, okay? So this is unknown, and now you see, you can annotate now as a comment here, you can discuss that situation like this. Save a 1, this is what you do, okay? Because later, you see, the set signal, you know, is deactivated, is 0 again, so now you have 0, 0, but now the system knows very well what exactly it has to remember, because 0, 0 is keeping the previous value, so the previous value was 1, so this is what you do up to this point. You see here, for this time slot, you do another operation from the table, from the function table, and this is, you know, keep the previous value. Then you will drive the R the same way that you did with the set. Now you are driving the reset, so now the function is like this. The system knows that has to go down, so low, you see, this is save a 0, and then you keep 0, 0, so this state is going to be kept that way. So keep the 0, that value, right? So save means, you know, write, save, store, memorize. Those are the words, that the verbs that we will use here. So it's a 1-bit memory cell, you see. The system is told to, you see, is told to save a 1, and this is done. And then the system is told to keep the 1 forever. But what happens later is that the system is ordered to save a 0, and this is what the system do. You see, goes to save a 0, and now this value is saved for another period of time, and then you can repeat that as well, because now it's exactly the initial situation. So now 0, 0, you see, it's again the same thing, 1 and 1. And you can annotate the same comments, memorize a 1 and save the value that was previously there, that was a 1. And then you see 1 and 0, and you go down to save a 0 again. And then something, you see, weird is happening here. You are driving 1 and 1, because you can do that, you know. At the inputs, you know very well that what you can have at the input is a situation like the as an electric circuit that is a push button that you call S. You see, S is a push button connected to the power supply, and then a resistor R connected to the ground voltage, so you can see that thing, and by means of a buffer, for example, this is your S. So this is the way you have to drive the S. You see, you click, you have a 1 when click, and if you release the button, you have a 0. So you can do that for both R and S, so no one is preventing you for activating the two orders at the same time. It has no meaning, but you can do that. That is what is this situation tries to mimic or simulate, something like this, okay? 1, 1, you click in 2 buttons at the same time. So in this situation, you know nothing, because you see, there's no way to know. It's not defined. The system can do whatever it likes. There's no prediction here. You see, it goes to an unknown situation, you see? So if this circuit is becoming part of, as a component of a larger circuit, that is indeed a great complication, because you know nothing about the value of the Q. So you must prevent that situation. So then you do something like this. You see, this is what you try here. 0, 1, so now you kept a 1 like this. So this is safe, a 1, no problem. And then you 0, 0, you keep this 1 like that. You see? So that is the typical evolution in time of a simple 1-bit memory cell. So this may be very well the initial discussions on the specifications of a chip like this, that you can even consider reviewing or enlarging when you go to a data sheet and you see more or less the way the professional chips specify for this kind of 1-bit memory cell. The next step naturally is for another video. The next step is it's quite interesting. If this is what we like to design, how to do it, and at that stage, you know, how to invent. So how to plan, how to invent a cell like this, you see. And invent at this stage in the course means how to invent a cell like this, if possible, using the same methods that we've been using, and using combinational circuits from the chapter 1, because this is what you know from the previous projects. Okay, so that's it. Let's wait for the next video tutorial on how to plan an RS latch. I mean, let's try to deduce the internal architecture using logic gates, for example. Okay.